basically had you read those first two sections from 4 and 5 to set a kind of context. So here's the simple example that's used in the textbook, Poole and Mackworth. And this is a delivery robot world in which there are just 4 locations that the robot is moving between: a coffee shop, a mailroom, a lab, and an office. And the features, the 5 features that describe each state, are the location of the robot. It could be in the lab. This is a 4-valued feature. Whether the robot has coffee. This is a binary feature. Whether Sam wants coffee, a binary feature. Whether mail is waiting, binary feature, and whether the robot has mail. And there's some actions, 6 actions that can be taken in this simple domain. The robot can move clockwise from the coffee shop to Sam's office, to the lab, to the mailroom, back to the coffee shop. It can move counterclockwise, the office to the coffee shop, to the mailroom, etc. It can pick up coffee, it can deliver coffee, pick up mail, deliver mail. So you've seen this. And the explicit state space representation, this is what a state looks like. It's just a feature vector. You'll see all kinds of symbols used for negation. But this says that the robot is in the lab, the robot does not have coffee, Sam wants coffee, mail is not waiting, and the robot has mail. Okay. The actions describe a transition between a given state and a resulting state. So after moving clockwise from this state, everything else, it turns out, will be the same, except the robot is no longer in the lab, but the robot is in the mailroom. So the robot is moved from here to here. And likewise, these are other states. These are other possible transitions using other operators, moving counterclockwise, delivering mail, etc. So just to set a little bit of context, the reason I had you read those first couple of sections from the earlier chapters is all the methods that we're talking about in chapters 4, 5, 6. We're going to be focusing on 6 today. Are going to use search. They're going to use the search methods we talked about last week. So they might use depth first search, breadth first search, heuristic depth first search, greedy best first search, iterative deepening search, A star, the iterative deepening version of A star. They might, any one of the tasks that we're talking about, be it from chapter 5 or 4 or 6, could in theory use one of these search methods. In chapter 4, it was about solving constraint problems. In 5, it's about proving theorems. Again, we'll return to those. And in this chapter, chapter 6 today, it's about planning actions. Actually making plans, again, making those plans and doing that search within a virtual space, okay, but with the intention that the plans or the paths that you're finding in search are going to be executed in typically physical space, but it could be elsewhere. And these are going to be pieced together, and you'll see a bit more in time, but today we're focusing on the search that goes on during this planning activity. So an AI system is planning to interact with the environment, and it's trying to figure out what it should do in advance of interacting with the environment. I think that's one of the strengths of AI, that focus on reflection before acting. This is the search this is the task that we're talking about today. But within each of those states, in chapters 4 and 5, they're basically going to be looking at, and you'll see this when we return to them. So, for example, theorem proving happens in a completely reflective way. You begin with a number of axioms in your knowledge base, and you prove or you enumerate. You might be asked to prove a particular proof or disprove it, but more often you are going to be in a position of simply elaborating or enumerating what follows from that initially given set of axioms. Nothing that you add to the database. If I tell you P is true and Q is true, you can make an inference that P or Q is true. You can also make an inference that P and Q is true. You can make a whole bunch of inferences from the basic axioms I give you. None of those inferences in the logic that we're talking about in chapter 5, and we'll be talking about more in a couple of weeks, is going to remove any of the truths, any of the theorems or axioms that were present from the beginning. Okay, it's simply enumerating what follows from the statements that you are initially given as true. You can imagine what chapter 5 is concentrating on then is what is present in one of these states that a planner is searching through. If I have an initial state, I know some things that are true, and from those statements I can reason about what else be true in that state. And so theorem proving might happen within this initial state, because you may have operators that you want to apply, and those operators may not depend on features that you have been explicitly told exist in this state, but may depend on things that you infer must be true in this state. And so if you remember your strips operators and preconditions, you may make inferences about what exists in this state. But once in your planning search, you make a move. You make a change in the knowledge base because your operators can make those changes. They can take a condition that was true and they can change it. The robot was in the mailroom, now the robot is not in the mailroom. It makes that change with each step here. The state of the world changes, and within this context, a new set of statements follow as true from what you are given. So what you've talked about in chapters 4 and 5 are reasoning technologies that would happen within each state of a planning system. Before the planning system knows what operators can be applied at a particular point, it may reason about what it knows to be true within that state. All right, and again, we'll come back to this, but I just want to set a context for how 4, 5, and 6 relate to each other. All right, 4 and 5 are about reasoning about what you know, and there is nothing that is going to be discussed in 4 and 5 which is concerned with changing the state of the world. Planning is concerned with changing the state of the world, so that you can still use those theorem proving technologies, but they will happen within a single state of planning. So, we've been talking about the explicit state space representation, and this can be cumbersome, and the book talks about this. Even for this simple example, over 5 features, we would have 4 plus 2 times 2 times 2 times 2 times 2 states. Possible state representations in this simple case. If you get to realistic situations in which you might have hundreds of features, it is simply too costly to reason explicitly from an explicit representation of the states. And so there may be too many states to reason about directly. It may be fragile. So if we want to add a feature to this representation that says, that keeps track of the projected battery remaining time on the robot's battery, we want to add that feature, and we want to add another part of the world that is a charging station. for the robot. Now we've got to redesign the state space. We've got to add these features and the state of the robot explicitly to the vector. And there's no explicit pattern here. There's typically structure in the world that we would exploit, that a real robot would exploit, but this explicit state space representation simply is given may or may not give us intuition as to what those explicit patterns are. A good example involves SAM 1 and coffee. We might come to that. We'll come to that in a moment. So this is an enumeration of the states that we've been giving and the transitions between those states. I do want to talk a bit about an aside. It might be relevant to the project, particularly the advanced part. We can use a very simple form of machine learning to structure these representations, to learn patterns from these representations. So if I simply take these representations of the transitions of actions, and let's say I walk through a very simple kind of machine learning here. This is stuff that psychologists were studying 50 years ago or more. These are algorithms that were perhaps the first algorithms defined for human learning and then AI learning. But you just take a look at this. So this is basically one thing this is one data row right here. Here's another data row. And it includes, each data row includes the state before and after and the action that's applied. So let's say that we have some very simple learning technique that gathers up like actions, and it does a very straightforward kind of generalization. Let's say that I walk through these one at a time. And this is one particular algorithm that was one of those algorithms that was studied 50 years ago. So I take a look at these two rows right here. I take a look at those two rows, and it looks like all features, if I look at corresponding features in these two rows, they all look identical except this one. This one is, in this position, these are different. Both involve MC. These are the same as well. The same here. But these are different. One general learning strategy might be, okay, let's generalize over these two instances. The things that match, we keep the same. So I'm going to get a row in which the result is lab. I'm going to get a row in which the second argument is RHC, the third argument is SWC, fourth argument is MWM. But then in this fifth row here, these are different. I'm going to replace this instance with a variable. And I've called, in this example, this variable might be called V1 if it was the first variable I generated, but I'm calling it V4. These two things are the same, so the operator is the same. These two are the same, MR. Create a row for this. These two are the same. Maintain RHC. Maintain SWC, MW, and these are different. And rather than replacing these with a different variable, I recognize that that RHM is the same as that RHM, and that not RHM is the same as that not RHM. So whatever variable I created for this fifth item here, I retain that for this fifth item there. So forget about the order in which I generate these variables. I call that V4, and so this is also V4.